How good were the croissants? I had two. Anyone else? Yeah? I thought I got like the second last one, and then like I turned around, there was like another mountain of them. It's like, I should come here every 2 years. Cool. Well, we've got some awesome speakers for you this afternoon, or late morning and afternoon. A couple of quick things. One, when we're presenting up here, I know it can be a bit tricky with the sound. So future speakers, if you're interested in grabbing a mic, feel free to grab mic. Just flick on the on switch. I can come and help with that. And also for those in the audience, if they are using these, and you can't hear whatever they're saying, give them a wave, give them a shout in case you can't pick up what they're saying. So let's all do our best and see how we go. But without further ado, I'm very excited about the next speaker. We have Michael Sexton, and he is the Acting Critical Minerals R&D Hub Lead at Geoscience Australia. So let's give a round of applause to Michael.
I'll try with one of these. This work?
Yep. We can swap. There you go.
Cool. All right, does that work? Yep, excellent. All right, I am the Acting Critical Minerals R&D Hub Lead, but by the end of the program, I will be the longest serving one. So how much acting is there? So what I'm here to do is give you a perspective on Geoscience Australia's activities in critical minerals. This will be fairly broad brush, kind of high-level program activities we're doing, and then maybe diving a bit deeper on the some of the R&D challenges we've experienced in those activities. So what I'm going to lead off with is a slide that we usually put at the end of our talks, which serves as a reminder to our audience that all the great science we do has overall objective economic value and impact, but I won't put it right in the front because what we're talking about is the value of what we're doing and the nature of the collaborative value of what we're doing. This is to emphasise two things, both the value, but also that the benefits of collaboration up and down the critical mineral supply chain. So when we're talking about critical minerals, it's not just about the earth science that we're doing, it's also further into the mid and downstream challenges that we need to understand as well. And that's where GA and CSIRO in the room have an active role to play. This slide was work commissioned from Deloitte Access from Deloitte Access Economics to estimate the value of pre-competitive geoscience done by government. And what they found was that for any dollar spent on pre-competitive geoscience, there was around $80 exploration supported, and then a further $1,000 of resource extraction, so 1,000 times multiple. Before I went on stage, I was talking to my colleague at CSIRO, Sandi Occhipinti, and she gave an example of ASTA maps that CSIRO had done work on. I think they spent about $1 to $2 million, and that has proved to be nearly $500 million of overall value. So you can see that this work has a really strong leverage. This is not just assessing the work done by GA or national organisations, but also state and territory surveys, and can include what is achieved by organisations such as AuScope. And we believe that if you looked at it from a collaborative point of view, that leverage would even be higher, so we get more out of our collaboration. So we'll do a quick overview of the geoscience programs for critical minerals, or initiatives that we're part of. The first is Resourcing Australia's Prosperity Initiative. Many of you will have heard of this, but for those who haven't, it's a $3.4 billion, 35-year investment into government geoscience that will provide foundational data sets for critical minerals discovery, as well as national resource assessments, which includes mineral potential maps at the national scale, of Australia's 35 critical minerals and strategic materials, and will involve deep collaboration with lots of science organisations and our partners in states and territories. There's also the Critical Minerals R&D Hub, which is a collaboration between GA, CSIRO and ANSTO on the technical challenges across the upstream and downstream value chain for critical minerals. And then lastly, I won't speak to this much, but I can take questions on it afterwards, is the Critical Minerals Mapping Initiative, which is an international collaboration on critical minerals, which involves the USGS, ourselves at GA, and the Canadian Geological Survey. And this is essentially a critical minerals in ores data set, is the most important feature of this collaboration, which is a global geochemistry data set for critical minerals in ore deposits. So A brief overview of our achievements in the Exploring for the Future program, which concluded last year. We covered the entire continent over 8 years on a number of different surveys. So you can have gravity surveys, AEM, all those lines are basically airborne electromagnetics. Yeah, so lots of activity. It concluded last year, and the result was that the government announced Resourcing Australia's Prosperity. So I have copied this slide verbatim, so the theme has changed. I'm pretty sure our designers at GA would be pretty mad if I didn't keep the livery used for the initiative. But this work can be split into 4 key components. The first is regional deep dives, where we will conduct 12 detailed studies of highly prospective but underexplored onshore regions, and these are being selected in consultation with key stakeholders, including our state and territory partners. There's a data and engagement part of this work, which will recognise how we deliver our data and engage with our stakeholders to show our important geoscience off. But really, for the critical mineral space, we're going to be doing national resource assessments that highlight the discovery potential and development potential for all of the critical minerals and strategic materials, as well as other opportunities in things like green steel, hydrogen, and energy storage. I'd like to talk in more detail about one of these 4 components, where I personally think we deliver some of the most impactful work at the national scale. So understanding Australia's geology and resource potential at national scale has never been more crucial. We will be developing Australia-wide geoscience datasets, as well as enhancing the ones we've already delivered, that span our understanding of the Earth to the surface, deep Earth to the surface, across a range of chemical and physical interpretations. The top row shows some of the national data sets that underpin most of the mineral exploration in Australia, and we'll continue to improve, update these, get higher resolution, expanding into frontier regions, and improve what we can with new technologies. And the bottom row shows some of the more recent national scale data sets, including the largest airborne AEM map in the world, which we'll then be filling in over the life of the program. It's at this scale where we have a unique offering, globally even, and collaborating with our partners like CSIRO, and we will continue to do this. But to really drill down on critical minerals, so the overview for critical minerals in Australia is, it's great to have long-term programs to discover them and talk to the science we're going to be doing over the coming decades. But when it comes to critical minerals, the challenge is a little bit more urgent. We're talking about supply chains that are restricted right now, and it's not just reliant on our geoscience, which will help discoveries decades into the future, but how we can fix supply chain issues currently. So there's challenges both up and down the supply chain. In Australia, there's nearly 500 deposits with a critical minerals resource. Of those, only 47 are operating, 30 or so are in development, and another 41 on care and maintenance. But the remaining 3/4 are undeveloped. So we actually know pretty well where these critical minerals are, how big they are, where we can get them. What we're not as good at is developing them into mines and then turning those resources into metals and products that can be used in the supply chain. So this is where the Critical Minerals R&D Hub plays a role. The hub was established in October 2022 with funding of $50.5 million until the end of June next year. The CSIRO hosts the hub, but each agency leads on specific projects, and these are the projects here. So there's 7 projects. The first 2 are related, but not done necessarily in collaboration, although I'll get to how there has been collaboration in a next slide. And this is on high purity silica and high purity quartz. So what Geoscience Australia is doing is, it's never really been done before, because quartz is typically seen as a gang mineral. No one's really interested in that, it gets chucked out. But it turns out, yeah, you have a pretty good use for it in semiconductors. And the issue is with high purity quartz, or that feedstock, is that there's only one deposit in the world that's producing the right silicon or the right quartz for silicon production, and that's in the US, at North Carolina. So we need to diversify that supply chain. If that goes offline, we're in a bit of trouble in terms of the feedstock. There's also very difficult to turn that quartz into silicon. It's a challenging process. So ANSTO is bringing their expertise there. for the downstream. We're also leading, Geoscience Australia is leading on a mineral criticality assessment, so to see what drivers influence critical minerals. So from a strategic point of view, how concentrated and at risk the supply chains are, and also the economic significance of those minerals, so what kind of value add does it add to the GDP. There's our byproducts project. This is a really good collaboration with our industry partners in Australia. So we've got a few zinc smelters and lead smelters in Australia, and what we're looking at is how we can recover gallium, germanium and indium from zinc ores. We know they are present in those ores, but we don't know what concentrations because it's not typically reported by exploration companies. It's not in their interests to report those numbers just because they're not a resource. And then so from point of deposit all the way through the supply chain, we don't really know where germanium and gallium and indium are going until they're taken out at the processing step. And that usually ends up in some country where they don't actually have germanium. I think we found that the French were producing indium, and we know there's no deposits of indium in France, so where did they get it from? We don't know. This piece of work is to understand where they are in the deposits, where they can be recovered, so this is work ANSTO's doing from smelters domestically, and also what techno-economics can be used to improve those processes, and CSIRO are doing that. There's the rare earths project. This is being led by ANSTO, so improving rare earth separation. Geoscience Australia is doing clay-hosted mineral potential mapping, so understanding where for these clay deposits they might be in Australia. They're actually mostly found in tropical regions, so you can find them in China, I think Madagascar and Brazil. We want to know if they are in Australia, if they're present here, and how can we find them better. And last two are led by CSIRO, so a high purity alumina process, which you can take any feedstock from what I understand, but turning it into high purity alumina is a very difficult process. And then the metallisation work that CSIRO and ANSTO are doing for lithium, rare earths and tungsten. So these are actually quite difficult things to metallise, and essentially China has the lead on a lot of these minerals for turning them into metal. So I'll go into what I think is the most interesting outcome of this that wasn't an expected outcome of the project, which is in the high purity silica, high purity quartz project, and the analytical challenges that are the same in the upstream and the downstream. So for high purity quartz, there are max concentrations for certain impurities that you can't go above, otherwise it's not suitable for the downstream applications of high purity silicon. And some of those, like boron and phosphorus, are actually, for most analytical techniques, below the detection limit that you can find them. So to actually assess something as high purity quartz, you need to use very, I wouldn't say bespoke, but not readily available techniques, such as X-ray absorption spectroscopy from, say, a synchrotron, that is not necessarily widely distributed and available to exploration companies, other researchers. And if you do want to get access to it, and there's a long lead time, so to do this research within a 4-year program, you might not be able to do it. But this is true also of the other side of the story for making the silicon. To know that you produced high purity silicon, you've got the same analytical challenges. So what we discovered through this work was that our geochemists and our process chemists had the same challenge, and there was nothing that they could really get available in their hands to solve it. So I think this is more about the analytical challenges, so it's not just an issue of purity. Quartz can be hard to analyse using all of the standard techniques that we kind of use out there in the field. And there's limited onshore capability. So one of the things I think I'd like to maybe have taken away is that government geoscience supports the Australian economy. Geoscience Australia will invest $3.4 billion into pre-competitive geoscience, and critical minerals R&D challenges really benefit from a whole of supply chain approach. And so many of the supply chains across this, many of the challenges across the supply chain, necessitate further research and infrastructure investment. So I think if Australia has ambitions to become a manufacturer and start making these critical minerals with high purity requirements or very niche or bespoke needs, we need to have an analytical infrastructure to support that. It's not just going to be piecemeal and done in one person solves it, another person solves it, different parts of the supply chain. It has to be done holistically. And if we're thinking about critical minerals especially, the main driver for critical minerals is that there is one country that controls the supply chain, and they treat this challenge holistically. They don't just tackle one part and say we've solved rare earths extraction. They treat the whole supply chain as a vertically integrated supply chain. They have the analytical infrastructure to do everything they need, and they don't just do it piecemeal. They do it properly. So I think it's kind of a whole of industry approach, a whole of government approach to solving these challenges is needed. And that concludes my presentation. Thank you.
Do we have a minute for any questions? Yes, down here.
Hi, Michael. Look, I know there's a huge debate around what elements are on the critical minerals list, what are strategic, and so on. But with regards to Australian interests, I'm coming from a Queensland knowledge here. We have a big region of vanadium,
yep.
and then likewise there's some success stories with graphite. So I'm just interested in the logic behind why those things are not being considered on your priority list in the list that you.
Both vanadium and graphite are on the critical minerals lists. I suppose why they weren't chosen in this initial part of work, and there's talk for ongoing parts of the program, what can be done, is these were identified as having gaps essentially along the whole supply chain in many cases. So for high purity quartz or silica, we don't really know where those deposits occur in Australia. So we wanted to know that. And then ANSTO is building a high temperature chlorination facility to do that. It's going to, if they succeed and deliver on time, it'll be a sovereign capability we didn't have before. So it's kind of to uplift parts of the supply chain where we know we have gaps. Vanadium, we know that, but there is ongoing work at CSIRO. They've got the Taiwan process that they've pioneered. So there's a lot of other R&D, so we want to make sure we're not overlapping with existing R&D as well. And there are things that maybe not quite at the scale needed to produce these minerals, but they are somewhere in the TRL that's advanced enough that you can expect it to be in the next 10 years. So I think that's probably why we didn't do those ones.
How good. Well, thank you so much. And we have our next speaker coming up. So we have Brad McInnes. Let me see if I can figure it out. Nope, I have not been doing a very good job with that. There we go. All right, love it. So we have Brad McInnes, Brent McInnes, my apologies, who's the director of AuScope's EarthBank project at Curtin University. We can do a mic swap if you like.
Okay, that's fine. Yeah, great. Good morning, everyone. Thank you for coming. Yes, I want to talk today about the EarthBank project, recent AuScope addition to the family, and the work we've been doing when collaborating in multiple different domains, including with the GPlates group out of Sydney. So the EarthBank project, what is it? We're a project, we've got 11 universities with geoanalytical facilities, and analytical infrastructure was just spoken about by the original speaker before me. We have 11 university geoanalytical facilities partnering for the first time, so it's a major collaboration, never before achieved in Australia. These facilities, so far our count is that they manage over $120 million in laboratory infrastructure. And they're the training centers for applied geochemists, PhDs, and EMCRs. This is the future for research in geochemistry in Australia, where these people are trained. And we provide analytical services across the board to industry, geoscience agencies. For example, in WA, the Geological Survey of Western Australia uses almost all of our facilities. They don't need to have their own laboratories. They can focus on their mission, which is to map the West Australian state, and we can provide them with the data to help with that. And these universities, of course, as you know, are a nexus for international collaborations in earth sciences. And our project has been quite successful in forming collaborations with other geochemical data groups, such as EarthChem in the United States, GFC in Europe, and with the NASA Astromat program in the United States. So overall, it's a very powerful group. And what are we talking about in terms of geoanalytical facilities? Well, I've got a picture here of a mass spectrometry lab at Curtin University, which AuScope provided funding for in 2014. It's called the Geohistory Facility. And this is the type of facility that I'm talking about now with EarthBank. We have every university with facilities like this working together and collaborating to make sure that the data we provide, that AuScope can support,
Bit closer. There we go.
that AuScope can support is actually worked on under a level playing field. So what is our mission? Our mission in this project is to build a national digital ecosystem for geochemical data that includes making sure we have modern laboratories, we have highly skilled researchers, and we want open data platforms for connecting samples, data, and people. So we have three programs. We've got, so far, we've got $22.6 million in funding committed. We have an enabling technologies, which is about making sure that decadal instruments, workhorse instruments in these facilities are replaced on a timely fashion. And we also, in terms of enabling technologies, we have a digital platform called the EarthBank platform, which links the labs, the samples, the data, and the people who work in those labs. Our majority of the funding that we are allocating is in the what we call the research data excellence space, and that's about people. That's about attracting and retaining data specialists and graduate interns into the EarthBank project. And we make sure that we provide these people with professional development opportunities and ability to access any of the labs that they may require outside of their domicile. And then a minor amount of the money, approximately $2 to $2.5 million, we expect to be residual, will be spent on impactful collaborations. And we're really supporting continental scale sampling and sort of deep analysis of the Australian continent via drilling programs. But we also want to make sure that if industry needs to use our facilities, that we provide them with some sort of a voucher to access the facilities and generate data from their drilling. That's not good. There we go. Yeah, so what are the principles? The principles are that we are collaborating. This is four principles that we've all agreed to. And this is basically our compass in the wind, if you will, where we can work out what we should be doing. So we want to make sure that whatever we're doing, we're working with stakeholders across the country to produce, deliver, and manage geochemical data at scale, a scale that's never been before achieved, and for societal benefit. We want to make sure that our data adheres to fair and interoperable principles. We want to make sure that these data models and data sets are developed by the world experts that exist here in Australia. And we obviously want to make the data that we generate in our labs openly available after publication. So we're trying to encourage people to upload their data sets, and we'll keep them private for the first 3 years. And that will protect the integrity of their ongoing research. But after that time, we want to make that data publicly available. And not everybody has a chance to publish their data in 3 years. And so we will actually offer extensions if necessary. But at the end of the day, this data is being generated with public funds. And so the public has a right to expect this data to be made publicly available. So at the end of the day, though, the sustainability of this project relies on us delivering a useful product. And so I want to be able to try to explain to you how we're doing that across the country. So here's the sort of the EarthBank project team. It's expanded by a factor of 3 since we started the initial project in 2021. But basically, there's spaces for both young career, early career scientists who are really growing up in the program to become the future leaders of geochemistry in this country. We've got a couple of blank spaces. These people have been selected, but they haven't got their visa to come into the country yet. But by the end of the year, we hope that this graphic will be filled up. And so in terms of the collaborations that I can prove and the data governance mechanisms that we put in place, this is a number of analytical techniques where we've brought together experts across Australia and overseas now to build data models which are put together. So uranium-lead dating obviously is a cornerstone of all geological survey missions, but also the later techniques that have been developed, such as hafnium isotopes and crustal residency times, argon-argon, fission track. And this is a paper that was published, actually it says 20 November, so it hasn't actually been published yet. It'll be published tomorrow, I guess, in chemical geology. And this is a work by young Angus Nixon at Adelaide University and a bunch of the EarthBank team, where for the first time we've actually put together a data model for major and trace element data. And believe it or not, that does not exist on the planet until now, until this paper. So this has been a great accomplishment. And what's happening with the platform itself, so this is a peek at the platform, EarthBank Online. We've currently got over 1,000 registered end users, and now you no longer need to register to use the platform. You can actually, under open access principles, you can actually access data sets and download them without registering. We've got a mix, both industry, government, and university people who are registered, and we have over 138,000 samples registered as of yesterday. We've been working with e-research providers across the world, such as MinDat, the IGSN consortium, and so forth, to make sure that all of our data systems are compatible with international norms. And we've just recently received both accreditation by the Core Trust Seal and the World Data System Program for the EarthBank data platform. So the impactful collaborations that we want to generate from this work are being inspired by the grand challenge placed to us by Geoscience Australia a number of years ago in building the Isotopic Atlas of Australia. And this is important because these isotopic maps can help you define terrain boundaries, cratonic boundaries, where mineralization tends to be predisposed to occur, because those are areas where you can have large fluxes of fluids and melts under the right circumstances. We also are looking to work with state and federal government agencies who are incentivizing their drilling programs by providing co-funding. We want to make sure that with EarthBank, we're able to support the industries that are drilling these holes by providing them with characterization and geochronology and isotopic fingerprinting techniques for all that material. We think that that's the best way for us to be supporting, again, state governments who are trying to support critical minerals exploration. But in terms of critical minerals, I wanted to talk about some recent developments that we've had with collaboration between our industry partner, Lithodat, and the EarthBite group. And this has actually been facilitated through an Australian Research Council linkage grant, in addition to the funds that EarthBank has been working on and providing. So this is about actually taking the GPlates platform and creating a time machine where you can place your samples. The samples here are, this is over 130,000 different samples which are currently in the platform, and how they plot against the continents 160 million years ago. And so it's pretty fascinating when you can do this, and you can automatically start making lines of inquiry about, well, if that sample was there, where was it relative to Africa, and that sort of thing. So this is a really important tool for understanding where geological samples are, but also for ore deposits. And so that's where I'm going to move to next. in terms of critical minerals. So, excuse me, on the left is a graph that's been recently put out by the IEA on critical minerals. Now, I'm not going to talk about the military applications of these minerals. I'm going to talk about specifically for the elements that are needed for the energy transition that many governments have signed up to, including ours. And of course, you can see here in the graph on the left a number of the elements named there. But the key issue is that over 70% of these elements are actually controlled by China. And yeah, so that's a critical issue for us in terms of a sovereign supply and the need to make sure that we can generate our own in the times of crisis. And the USGS has just named copper for the first time actually onto this critical minerals list. And just to put it in perspective, the globe consumes 20.7 million tons of copper a year, according to this Visual Capitalist article on the right-hand side. I think it's actually higher than that, it's about 22 to 23, but I think about 10% of that comes from recycling. But anyway, you basically need to mine 20 million tons of copper a year to meet our current demand. And this is another graphic put forth by S&P Global in terms of the economics and why we need copper. And so what you have here is this line here. This is the actual projected production and supply of copper based on the resources that we know. And by 2040, that's expected to, this is 2040 here if you can't read it, that's expected to double. And the key drivers of this are net zero policies. And it's not about windmills or solar panels that are consuming this. It's about actual connecting these things to the grid and electrifying transportation. So, I mean, the crazy thing about this is to fill this supply gap, we need to develop 30 supergiant deposits in that time. And I'm talking about Olympic dams. That's one Olympic dam deposit that has to be discovered and developed every 3 months for the next decade. It's crazy. It's just impossible. And it's a good time to buy BHP Billiton shares or anything, any copper share, because at the end of the day, there's no doubt about it, the price of copper has to go up. So we want to focus on copper, and here's how we use the GPlates program to do that. This is a representation. This is extracted from the USGS database, all of the copper deposits known in the Tethyan Belt. And so the color scheme represents, there's 128 deposits. Color schemes represent anything that's in blue is the oldest at about 99 million years, and red is about 3 million years. So I can make a video in EarthBank and show how these are actually forming. Yeah, so you can see the porphyry copper deposits forming as the Tethys Sea closes, as Africa smashes into Eurasia. And what we want to do with this is try to understand what are the key points, in terms of the subduction process when you start to form these copper deposits. And this, for the first time, is our ability now to both look at orogenesis and plate tectonic reconstructions. And this is facilitated by the AuScope program. To put it in a slightly different context, this is this map speeded up, but I'm looking on the right-hand side of this graph is the amount of copper that's being endowed in the crust. It's fertilizing the crust. And you can see that there's two key gaps here. Over here, whoops, sorry. There's two key gaps, one around 85 million years and one here less than 20 million years. And what are the key issues that are happening during that time? Well, we've got oblique subduction happening around 85 million years, and we've got increasing rate of conversion and continental accretion. And a continental accretion seems to be a very critical part of generating large volumes of copper. And what we're talking about here is that in terms of the total endowment of copper in the Tethyan belt, it took 100 million years to generate 80 million tons of copper, and we consume that in just 4 years on planet Earth. So this is a real crisis for the world to work on. And machine learning using these techniques is something that the EarthBank group has been working on with us. This is some of the recent examples of a paper published in March looking at porphyry genesis in, thank you, I'll be with you, happening in Papua New Guinea. So yeah, this is where we're going to go with machine learning, and also these are the number of factors that are involved with that process, seafloor spreading rate. These are the more you are to the right-hand side, the greater the control in forming porphyry systems are. So this is the first time that this has been looked at in this circumstance. What we're seeing also is now new data models that go back to 1.8 billion years ago. And we want to make sure that this copper time machine can go back that far and use it in that way. And so this is a paper published last year by Adelaide and Sydney groups. And here you can see 1590 is when Olympic Dam formed. The magenta pink units up on the upper left-hand side, that's Australia. That's Proto-Australia forming. And we want to be able to look at this model in terms of copper prospectivity and other prospectivities for critical minerals. And to do that, we need a national research infrastructure that's capable of generating large volumes of data, and that is what the EarthBank project is designed to deliver. So thank you very much for your time, and happy to take some questions.
We might pause on the questions until we've got a panel after this, so thank you so much. Let's see if I can figure this out this time. Here we go. Love it. All right, there we go. We do have, coming up here, we have Shane Mulé, who is the project leader of the National Virtual Core Library, or NVCL, at CSIRO Mineral Resources. You're already mic'd up? Let's go. Let's see what happens. Let's start with a round of applause.
Hi, everyone. Yeah, so as already been mentioned, I'm the project leader of the NVCL, or National Virtual Core Library. I'm here today to present on some perspectives and opportunities that we are enabling through this project. Before I start, I'd like to acknowledge AuScope, CSIRO, and the 6 Australian geological surveys, without which this project wouldn't be possible. So as we know, the minerals industry is highly volatile, and commodities prices change over time, influenced by everything from supply shocks, natural disasters, conflicts, and political landscape. And we also know that opportunities can arise unexpectedly, and for industry to capitalise, they need to respond quickly. And to do that, they need the availability of useful and impactful data. An example of this is the recent critical minerals deal signed between Australia and the United States, which seeks to invest $8.5 billion US, of which $1 billion is slated for spending over the next 6 months. Of the 2 priority areas, the Afura Nolans project, highlighted in green, is already represented within the NVCL. So our data is inadvertently going to be used to support the future development of this project. This highlights how NVCL can be used to respond to challenging priorities and often short-term funding requirements. The NVCL can be queried for any commodity, is adaptable and free for access and use by anyone. So what is the NVCL? The NVCL delivers the world's largest publicly available mineralogical data set. It provides scan drill core for the top 1 to 2 kilometres of the Earth's crust. As I said, it's funded through NCRIS, through AuScope, CSIRO, and 6 Australian geological surveys: New South Wales, Queensland, South Australia, Northern Territory, Tasmania, and Western Australia. We also collaborate with Geoscience Australia and Australian universities, and the instrument is developed by an Australian manufacturer, CoreScan. We deliver across 4 pillars, going from material infrastructure, which in this case is drill core, utilising technology, as I mentioned, human infrastructure, so interaction and outreach and collaboration with industry, government, and researchers, and deliver that data through fair platform for anyone to access. So why do we have an NVCL? So the Australian resources sector spend tens of millions of dollars a year on drilling. Often this is done for a single commodity, and when deemed financially or unfinancially viable, the core is often discarded. Some core does make its way to core libraries, but often this data is not sampled sufficiently. Additionally, the hope to be able to reduce the number of drill holes that we're actually drilling by getting more information on the drill holes we have and better planning our drilling campaigns. Traditional manual drill logging that's done is quite subjective, so manual interpretation is subjective and quite cost intensive. And the idea here is to try and reduce that subjectivity and bring some objective analysis of this drill core. Mineralogy was chosen as the key parameter that we want to measure because its impact across the value chain, and it's also rarely collected. As you can see in this is a flow chart just kind of just presenting how the MVCL essentially, well, how things work. So we start with the top panel there, where Australian companies drill millions of metres of drill core every year. And of that, a subset, depending on state and territory requirements, gets sent to the geological surveys, and they maintain tens of millions of metres of core in their libraries. And a subset of that is sampled using the high-logger instrument that you see on the top right there, which is an instrument that was originally developed at CSIRO back in the early 2000s, and thanks to MVCL, was then deployed to the state geological surveys, and is now, has since been commercialised with an Australian company who develops this instrument. And the surveys scan somewhere in the order of 10 to 100,000 metres of core a year. And then after scanning, that data gets put onto the MVCL through multiple portals, primarily the AuScope portal, for access by the public. We've currently got over 6,000 drill cores in the repository and 1.5 million metres of scanned core, and this is growing every day. The goal really is to deliver fair data in the end, which is via open portals, both AuScope, but also the state geological surveys and other portals. So the high loggers, where are they? So as you can see in this image here, the 6 geological surveys that I mentioned each have a high logger 3 unit, which was originally developed at CSIRO and deployed thanks to MVCL. And 3 surveys currently have a high logger 4, which is the new instrument that was developed by an Australian manufacturing company. And thanks to ongoing support by AuScope, we're hoping that we get 2 more states on side in the next coming years, with the hope that all will be online with the new instrument, because the old instrument is coming to end of life. So the hope is that we keep continuing this project going forward. We've had previous international collaborations in South America and Asia, so there are a couple of high logger units that are floating around the world, but most of them have reached end of life. But we are in new collaborations with Canada and Europe about deploying new instrumentation and potentially about duplicating the MVCL concept in other countries. We've got a large focus on training, outreach, and case studies. So since inception, we've undertaken 61 domestic workshops across all states and territories and 3 international workshops. There's been over 55 domestic theses that use some MVCL data and 38 international theses. We published over 43 international peer-reviewed journals, had 2 Australian Journal of Earth Science special issues, and over 84 papers presented at conferences. And this continues every year. Now onto impact. So we commissioned an external review recently into NVCL and AVRE that are both funded through AuScope and run by CSIRO. And it found that the MVCL yields positive benefit to Australia by providing data and tools. It has specific impact on mining and geologic hydrogen, who use the mineralogy data and drill core data to better identify sites for drilling. Over the review period, they found a net positive benefit of $253 million, which equates to about a benefit cost ratio of 2.99, so $3 back for every dollar spent. We really try to make this as conservative as possible and realistic as possible, and we think that this reflects a conservative estimate of what this AuScope project brings to the community. In addition, looking at ASX releases, so there's over 50 ASX releases that specifically mention the use of MVCL data in mineral exploration success or discoveries. And critical minerals and strategic minerals already feature quite prominently within MVCL. The pie chart on the right there shows for the West Australian database the the reason drilled, the reason that the hole was drilled, the commodity reason that the hole was drilled. And you can see there's quite a prominence there of critical minerals that are highlighted in the red. And the table in the middle shows the increase in these commodities in the last 5 years, and you can see that the rare earth elements and platinum group elements feature quite heavily, over 100% increase in the last 5 years, which is in line with, I guess, trends in drilling and exploration. And the geological surveys work directly with companies, 10 to 100 companies, each geological survey each year, for drilling and analysis and interpretation of this data. So talking just one example for rare earth elements. So rare earth element hosted minerals can vary quite significantly over deposits, but they're often studied using point sampling approaches. So one of the things we've been working on recently is looking at if we can get a better understanding of the variation across deposits and across geological provinces, because that doesn't exist in public domain at this time. So on the image on the right there, it's highlighted some world-class rare earth element, critical mineral and traditional deposits, which we have data for within the NVCL, and that have been used and continue to be used by industry, government and researchers to better understand these deposits. And these provide opportunities for improving everything across the mining life value chain. So looking to the future, so we're looking to deliver across four main focus areas. So firstly, impact. So looking to improve our reporting and statistics so that they're clear, easily accessible, and ideally done automatically so that anyone can access them and understand what the database has and what we cover. Focus on standardization, so looking at a national standard data product. So we currently do have a somewhat national standard data product, but it's not standard enough. So improving that standard and also looking at complementary geoscience data, which helps the interpretation of that hyperspectral data to mineralogy. Looking at data integration, because the hyperspectral alone is not sufficient to be able to get a non-unique solution for some mineralogy. And so by increasing the amount of co-located data that we collect and we link up with hyperspectral data, we're able to improve the results that come out of that data. And lastly, looking at national products. So historically, the states collect the data and normally deliver products on a state-by-state basis. But there's a lot that can be gained by looking at this data from a national perspective. So we're looking at developing national mineral maps that hopefully in the future can be configurable for a user so that an industry partner or researcher can specifically identify depths or locations of interest. An example of that is some recent work that has been done at CSIRO looking at hydrogen potential, prospectivity. This work looked at looking at likely sources and proxies for hydrogen development and identified that olivine, pyroxene and siderite were the most likely minerals. And by looking at the depths at which these occur at all the drill hole locations, they're able to identify areas of interest that you can see highlighted in the black squares there as the regions for highest potential for hydrogen production. And this work is ongoing, but just shows an example of what can be done by providing, using the MVCL as a national product. Just in summary, so the MVCL delivers a net positive yield to the Australian economy with an estimated BCR of 2.99. It improves exploration outcomes and success across the mining and geological hydrogen value chains. It's leading to a reduced drill hole activity and greater use of existing drill hole material. The dataset provides free and adaptable source of mineralogical knowledge and can be applied to understanding mineral systems, prospectivity and direct detection of minerals. And it's already being used to find and understand critical minerals and will continue to as it expands. Thank you.
I think we're just going to carry on if that's okay. Great, love it. I'll get the next slide. Thanks again. Up, here we go. Thank you. So, yes, great. So we have Sandi. Sandi, I have some information that I need to read. Oh, I've got the wrong page here, Sandi. You don't need to. I don't need to introduce you, Sandi. Well, ladies and gentlemen, Sandi.
Thank you. Okay, so I wasn't sure what the brief was today, so I threw some slides together and let's see how we go, and hopefully it'll sort of ignite a bit of conversation going forward. But I want to thank the previous speakers because they've really framed this very well, and the slides that I deleted were pretty much covered by them, which is really nice. But essentially, in order to decarbonise our economy and provide technologies and materials we predict we'll need in the future, we actually need to find more metals. And we have delineated many of these in deposits like on the map that Michael showed, but I can guarantee you most of those deposits will not go to mine. And that's because of the quality of those deposits. Generally, it's very difficult to extract metals from them. So what I'm going to go through today with you is really just a snapshot of some of the work that CSIRO is doing in this space with others. It's definitely not all of the work that we're doing in it. But in order to, to frame this, I just wanted to show you how our reliance on metals through time has changed, and this is thanks to Jens, who put this slide together for me some time ago. In the 18th century, we mined these things, calcium, iron and carbon. That's all we thought we needed. 19th century, we added a few more elements to it. Now, this is not obviously including precious metals, and gold is king right now, I have to say. Don't know what the share price is today, but it was $6,900 an ounce last time I looked, I think. 20th century, we had an explosion of the metals that we needed to extract, and that's because we started to really understand what these metals could offer us in terms of their with their properties. So magnets, for example, in the critical mineral space, those really strong magnets. And then the 21st century, well, we've basically got to half the periodic table with the metals that we would like to extract in order to build those new technologies that we need into the future. And as Brent alluded to before, they're not just for the clean energy transition. Unfortunately, when you look at growth curves around the amount spent in defence and the metals that we need for the future, they mirror each other very nicely. But critical metals are often companion elements, so they come in very small quantities or sometimes larger quantities with other mineral deposits. And this is both a blessing and a curse. It's a blessing in that we've already mined them in many parts of this country at least and globally. It's a curse because it's very difficult when you try to process lots of metals out of the same deposit or the same minerals. Why Australia and what is our role? So we often talk about the future made in Australia. I'd like to talk about the past made in Australia. So these metals were made here. We have a long history from the Archean through to the recent times of actually concentrating them in the Earth's crust. And the why Australia is because Australia basically contains favourable geology, obviously. I'm speaking to the converted here, and 1.5% of the Earth's crust, basically. That's compared to Europe, with only 1.2% of the Earth's crust and many more people living there. So it's much easier for us to delineate and extract metals here for the Europeans than to actually do this in places like Europe. This was originally my summary slide, but I'm just going to give you a taste of some of the things that we're doing at CSIRO. So we're looking at quantum sensors or new types of sensing technologies and computing for more accurate geophysical models, downhole sensors from mineral mapping, pre-concentration driven by sensing and different types of sensing, low impact exploration through prediction, multi-physics for more accurate modelling. I've got something here that I've just called microgeology or microexploration. 3 to 4D dimensional geology and geometallurgy, so in terms of understanding that subsurface, and assisted decision-making. So almost everything we do now contains, every team that work in our sort of landscape has a data science component or a software engineering component as part of that team, or a data management component. In the short term, and Michael talked about this, what can we do? So in the short term could be 5 to 10 years. Basically, there are lots of opportunities in the short term to meet the demands ahead of us. So sorting waste from ore more effectively, or pre-concentration, cost-effective processing, new processing technologies, and better mining practice are all things that we are working towards. And I just want to really point out what's in the middle there, that micro-exploration. So geometallurgy, what actually happens most of the time now is that the geologists find a deposit, then they kind of go away. Someone else digs the deposit up. They basically just crush the ore and put it into lots of vats and make bubbles and try to get something out the other end. There's a little bit of geometallurgy done at some point, but they don't worry about the minerals, because chemists don't care about the minerals, they only care about the elements. And so they're not really perhaps optimising the processing part of the extraction process. So in terms of pre-concentration, one of the things that we do, we have a team at Lucas Heights that only looks at delineating mineralogy from rock. So, and that goes into ore sorting. That's our sensing and sorting group. They're currently working on pre-concentration of lithium via X-rays and or radio methods, so they might use both. There's obviously an issue with the X-ray method with lithium, but you can pre-concentrate, take out the waste from the ore that way. The radio methods will be able to detect mineralogy such as spodumene or other minerals, and then pass that through to be processed. They're also doing the same sort of thing with rare earth, but we're a little bit not as far along with rare earths. The problem with rare earths, obviously, is that you need very, very low detection limits, and so these are bulk ore sorting methods. So getting to very, very low detection methods with bulk sorting methods is difficult. We need a real-time measurement for that waste control as well. So just on that as well, just to go back to that, one of the things that's come out of this group recently is detection of landmines, okay? So this is the same technology that CSIRO is using to detect landmines in places like Angola, and will be going into Ukraine, I think, too, as well, to detect landmines. It's basically detecting mineralogy on the fly with sensors. High purity alumina, here's some work that we're doing through the Critical Minerals Hub that Michael introduced earlier, a collaboration between ANSTO, Geoscience Australia and CSIRO. Alumina is everywhere, but it's very, very hard again to process. You need concentrations of 99.99999% for high purity alumina. CSIRO has just developed a processing pathway where we're experimenting. So we start at the bench scale, so very, very small quantities, and we're just moving up to the kilogram scale to see whether or not we can process alumina out of just about anything. So it's any feedstock. You can imagine in the rare earth space, you could, rare earths from clays, for example, you could extract your rare earths out of the clays and potentially use the same material to extract alumina out of into the future. Now, when we go back to this micro-exploration idea, or the geomet sort of idea, one of the things that we can do is really understand where the impurities in minerals sit. So here's an example here of, well, there's two examples here, but I'm just going to look at the atom probe one up the top there, where you can see we've got alumina and silica, and the silica is really concentrated. It's right throughout it, but it's really concentrated in those dislocations. So understanding what the structure at the very micro scale looks like is really important for people processing or preparing the rocks for processing, because we may be able to crush the rocks in a different way or using different materials to crush the rocks in order to get rid of those deleterious elements. Value adding, so again, metallisation. So how do you go from a rock or a feedstock, a powder, to metal very quickly? Apparently you put it in a machine, just like this in the middle here, and you pass it through a machine at supersonic speeds. And at supersonic speeds, we basically move the atoms apart, and eventually they coalesce again together. At the end, they get supercooled at the end, and they basically form a metal. So here's an example of dysprosium. We've done this with magnesium already and commercialised that to a company called Maxonic. And we are doing this as well for lithium and hoping to do it for rare earths and tungsten. In the rare earth space, there's a lot of work that we've been doing with ANSTO and GA around rare earths in clays. Now, the reason for that is that we have found that there are concentrations in rare earths in clays in different parts of Australia where it used to be tropical, perhaps, but not now. So if you, they are not your typical ionic rare earths, but ANSTO is working on a way of actually extracting those rare earths out. We're using mineralogy with geochemistry and geophysics to be able to delineate where the most concentrated parts of these rare earths might be, and then we're more detailed analysis to really understand where they sit within different mineralogy. In the lithium space, what we have noticed is that when you go and study lithium pegmatite deposits, there's alteration patterns around and within those deposits that we can detect from space. So here's an example of some Prisma data from the Pilbara region. I haven't put on the little areas here, but what we were able to do with this study with a particular company was actually delineate where the pegmatites were that contained relevant mineralogy for perhaps lithium pegmatites that then they could go and follow up on. In 3D, and this is from the Rare Earths in Clay project, what we've done is looked at lots of geophysical data, including electromagnetic data. So what we're mapping here is the regolith in this region, and when you start to put all the data together, we can predict where the higher concentrations of rare earths are in a region in 3D. I haven't put a 3D model on here, but you can see the depth slices there, where we've been able to delineate upper transported cover, thickness slices, including saprolite and total rare, you can see the total rare earths coming out there. But the reason why we do this is it helps industry. We're developing workflows that will help industry do this work themselves. Critical mineral deposits on their own are small and they don't contain massive footprints. One of the things that CSIRO found many years ago, back in 2012, we produced the first ASTA map for Australia, and believe it or not, all the ASTA data are on that map, but it's very hard to see it because it's so sparse, really. What we found was that companies found deposits based on that ASTA map. So we were thinking, well, what if we produced a new mineral map or new mineral maps for Australia? What difference would that make? So on the right here, we've got some coverage. That was from about February. We've negotiated with the European space stations to be able to serve these data. Thanks. And we've now covered the whole country. So this is from about 2 weeks ago, I think. So we've managed to collect all the hyperspectral data across Australia, working with the European space stations. We will be serving this data through a platform called HIRIS at different resolutions for industry. And we'll be using these data ourselves to try to map out where these alteration footprints are around different types of deposits. Mapping light elements is obviously really important as well, and CSIRO developed the Maya mapper, or the Maya detectors for synchrotrons many years ago. We have a couple of Maya mappers within the organisation ourselves that can give you sort of geochemistry and mineralogy at the scale of 50 centimetres by 15 centimetres on rock. We are developing a system to deliver a femtosecond LIBS laser now to this system so that we can map down into the light elements, and also we'll be adding mineralogy sort of sensor as well to it to deliver fused products. For industry, so it's all well and good doing all of this work, but we actually need to translate what we do into tools that industry can use if we want to meet our energy transition problems. And I won't go through all of this, but some of the work we've been doing is that rather than just developing a technique that delivers a better result in the lab, we are using AI to also help us to analyse the data to be able to sort out anomalies from areas that aren't anomalous. The other thing we're doing is we've developed something we're calling our field SEM, and it's essentially a machine learning software solution where we've taken millions of spectra from TEMA or from SEM, and we've trained LIBS models to be models, so from LIBS data to be able to translate it. So that mineralogy image here in the lab takes 8 hours to scan. In the field, it's 8 minutes. And you can keep up with a drill rig in terms of returning the mineralogy. So geologists in the field will know what they're looking at. This is my last slide. So another thing that we are doing are looking at developing new geophysical sensors. And here's just a taste of this one, downhole quantum squid magnetometer. So the idea around this is that we'll be able to see further with our EM, less noise, and hopefully just better results. That's it.
Thank you so much. All right. I don't know about you guys, but these are the nicest seats I've ever had at a conference before. Like, just feels like I'm on first class of a flight. Not that I've ever been on first class in a flight. So what I'm going to get us all to do right now is to stand up, just very, very quickly. Stand up, because I'm enjoying myself too much in these seats. And then what I'm going to get you guys all to do is to pivot one way and just give a little side stretch. Everyone look at one wall, pivot the other way. Everyone look at the other wall. Give yourselves a little shake of your hands. And yes, we do. And we're going to sit down because I wanted everyone to be up and very excited for our next speaker. So here we have Graham Heinson, who is the Professor of Geophysics at the University of Adelaide and AuScope Earth Imaging Program Node Leader. Thank you so much.
Thank you very much. Well, good afternoon, everyone. I'd like to acknowledge that AuScope funded magnetotelluric instruments about 20 years ago and put significant investment into building what is now probably one of the world's largest pools of equipment. So I've written out the specs of all the equipment. You don't have to know what they are, but what I did want to emphasize is that that's provided a platform for about 30 PhD students over the last 20 years across maybe 6 or 7 universities. And I particularly wanted to shout out some remarkable people, Mr. Goran Boran, here deploying one instrument. Goran's been our technical officer at the University of Adelaide for 20 years now, supported by AuScope, and really everything I'm going to talk about afterwards would not be possible without Goran. So a tremendous facility. It's not just the equipment, it's the people that support it. So magnetotellurics as a field has kind of blossomed over the last 20 years, and there's been large investments and significant progress, particularly led by Geoscience Australia, but supported by just about all of the state and territory geological surveys and many universities. And so what I'm going to reflect on a little bit is the progress to date, and then really where we go from the future. So this is not quite definitive, but it gives a snapshot of roughly where we were 20 years ago and where we are now and where we're going in the future. So in the first early 2000s, the coverage of Australia with long period magnetotellurics and to some extent broadband magnetotellurics was very, very sparse, really just a handful of instruments across and one small grid in the western part of Victoria. So that sort of coincided with the investment from AuScope, and you can see in the sort of subsequent decade, the coverage with tremendous support from the state and territories, and particularly Geoscience Australia, then covered all of South Australia, Victoria, Tasmania, and then by 2025, you can see about half the country is covered by these measurements. So they're about every 50 kilometers. There's significant gaps in some areas. So about half the sites across Australia have been covered in the last, say, 15 years. And we made a pitch to AuScope about 2 or 3 years ago to say, well, if it takes another 15 years to complete the rest of the country, that's a long program, and by 2040, I probably will be playing golf and not be doing MT, and it would be lovely to see progress, to see if we can cover the country, even at a lower density. So we put the pitch to AuScope to say, let's see if we can provide a bit of a framework which we can infill later. And so what I've highlighted there is some boxes, and you can see in the left-hand box in Queensland, there's about 88 sites. So they are currently being deployed. We've got a team out today. They're picking up a batch of 23 instruments. They're spaced every 100 kilometers, but they cover that region from sort of the Mount Isa province to the coast. We're then hoping next year we will then move into Northern Territory, that northwestern part of Northern Territory, and then with time in the 2027s and beyond, is we'll partner, and Geological Survey of Western Australia are currently doing an amazing job with the WA array, and we will pivot to join with them to see how far we can get with covering WA over the next 2 or 3 years. But I'm hoping by this time next year, we will have complete coverage of the country from the West Australian border to the eastern seaboard. So the question is, well, why would we do this? Well, the reason we can do this is that it provides us a national framework, it provides a three-dimensional view of the Earth, and it provides context to large-scale crustal tectonic regions that you can't see from small grids, and you can't really determine any other way. So what I've done here is just shown a few images, and what I've done is simply take small regional models, so when I say regional, statewide size models, join them together so there's a little bit of mismatch at the joins, and the reds are the conductors and the blues are the resistors, and we're starting to piece together the electrical framework of the Australian continent. So I've shown here the highest level, 0 to 10 kilometers. We're basically mapping sedimentary basins. As we move deeper into the Earth, we can see big conductors that represent presumably graphitized zones and sutures. And then as we move further down in the crust, into the lower crust, we see these big conductors that branch out in various directions. And when we look at these, they really map the location of sutures from Paleoproterozoic accumulation and accretion of Australia. And so they really also define the edges of cratonic blocks. So when we map the whole country, we'll be able to sort of get a framework to understand really how Australia was joined together through these signatures. So I'm just going to give you 2 examples of what we can get from the electrical resistivities. We can see it in terms of resistivity, but what do we actually learn from this? Now, I'm just going to do the first one is more of a tectonic view. So these very enigmatic Cenozoic volcanoes, about 1,000 of them from the northernmost Queensland to the southernmost part of Victoria and into the eastern part of Australia. Beautiful series of volcanoes with no significant age progression. And if we invert all the resistivities, so there's about 800 sites of magnetotellurics gone into these models, we can start sort of stripping back down through the structure of the Earth. What I've shown on the top left-hand side is at 2 kilometers, and just put the basins on the top. We can really map out, of course, where the sedimentary basins are. They're electrically conducting because of the porosity. But we can see variations in age of the basins and how varying porosities they are. 10 kilometers, everything's resistive because it's basically dry silicate materials. But then when we get down to, say, 40 kilometers, what I've popped on the top of that are the volcanoes. So these are all the volcano centers. They're colored by age, and they really just plot directly above where the Earth is electrically very conducting. And these maps at 40, 125, 150, 200 kilometers, although they're maps of resistivity, they're actually maps of temperature. So you can map the temperature of the Earth from the electrical resistivity, and we can get a very almost exact match between where we expect the volcanoes to be and where the rocks are most hottest, and therefore they conduct the most. So that just gives us one insight into the Earth, but I'm just going to pivot a little bit to mineral exploration paradigm. The sites of AusLAMP, they're 50 kilometers apart. We've got broadband sort of MT sites which tend to be much closer together, 1 to 5 kilometers apart. They give us a broad outline of the electrical structure of the Earth, but they do define properties of the Earth which provide us indications of fertility for mineral provinces. So I'm just going to show one example here of the Eyre Peninsula, or the Gawler Craton and the Eyre Peninsula. And I've just shown it here as depth slices, initially 1 to 5 kilometers, and then down in the bottom row, down into the lower crust, 35 kilometers and deeper. So the big black outline, of course, is the Gawler Craton. You can see the outline of Eyre Peninsula, York Peninsula. Again, reds are conducting. They show porosity near the surface, and we can map out again the basins. But as we go down, we can see the Earth becoming more resistive in the upper crust. But within that framework, we start to see big conductors, and particularly on the northeastern part of the Gawler Craton, this is where we have the Olympic domain, and we have the deposits of Olympic Dam, Prominent Hill, Carapatina, and the newer ones, Oak Dam, Hillside, etc. And there's a very strong correlation between where these conductors are within the crust and where the minerals are at the surface. So we can see that as we move down even to greater depths, say 35 to 45 kilometers, and we can see the association with some of the gold deposits, as we've seen in other parts of Australia. And so this becomes a map of potential prospectivity, because essentially the regions that conduct electricity show a change in the crustal fabric. So this is an overprint. It's something in the crust that's become conducting, because silicates normally aren't conductors. And therefore, it indicates the zones where there has been perhaps fluid flow, there's been changes, there's been events that have caused that to be different in its electrical properties. And I've just highlighted one zone on the bottom right-hand corner, and really just this little inset of the zone over York Peninsula, the very kind of eastern part of Eyre Peninsula, and into the Delamerian in the western part, sorry, the eastern part. So again, the blues are resistive, the reds are conducting, and what I've plotted on top of those are the little red dots are all the copper occurrences. And you can see a very, very strong correlation between where the Earth is conducting at 35 kilometers and where those copper things are at the surface. But more in particular, the yellow dots are the copper reserves. So this is where copper has been kind of evaluated as a resource, and they tend to be more aligned with the boundaries. And so this is a paradigm we've all known that, of course, mineral systems occur often at the edges of cratonic regions, regions that change their property. And by mapping the lower crust, we can get some idea of the prospectivity of the upper crust. So we've applied this in various areas, and we find actually a remarkable correlation between the maps that GA have been producing with the IOCG predictions and these maps of lower crustal conductivity. So that's where I'm going to leave it with you. So that's hopefully time for questions, or we can go to panel. Thank you.
Thank you so much. I don't think we'll... Thank you so much. I don't think we'll do any questions, but yeah, thank you so much for that one. And yeah, very, very grateful, Graham. So we've got our panel discussion now, which is very, very exciting. Can we get Brent, Michael, and Sandi back? And also we're going to introduce Caroline. And I'm going to hand over to Tim, who's going to do everything.
Thanks, Dave. So we're going to sit down the front so we don't feel like we're at the UN or at a high court or something. And there are going to be opportunities for everybody to ask questions. Sorry, I'm just seeing how many chairs we've got. I'm going to grab one more.
Oh, we've got more people.
I'm going to sit off to the side like, I don't know. This is very Q&A. All right, so I would like to introduce Caroline Tiddy, who is our equal newest board member and is an associate professor at the University of South Australia, soon to become some other university, and works with the McInnes CRC, I always get to say the wrong one, McInnes CRC in their education division. Is that right? Pay that? Excellent. So look, I sent a whole bunch of questions to these guys to prepare them. I'm not going to be able to go through all those questions, I realise, because there's a lot of them. But I want all of you to be able to ask questions as well. So please, we'll create a space for you to all ask whatever questions you want of the panel. But the reason for putting this panel together is so that we have an opportunity to talk about why we should be working in critical minerals, why AuScope should have a focus on critical minerals. We've got board members in the audience. It's great for us to try to get that message across, so let's have a conversation about that. And what the opportunities are for us. So I'm going to start with my first question. I'm going to ask Caroline, since she is the only one that hasn't spoken yet. So I guess for all of you, please think about from your discipline area or your organisational perspective, what you think the research opportunities are in the next 10 years. And what the opportunities are for AuScope. So, you know, we've heard about from Geoscience Australia's point of view and from CSIRO's point of view. What I'm really talking about is that research focus, that national research infrastructure investment. So what are the research opportunities that are emerging and what investments should we make in the next few years to enable that? Caroline.
Thanks, Tim, and thanks for having me here. And it's lovely to have this new position within AuScope on the board. So in terms of what I think the research opportunities are within the critical mineral space, there's actually, I think, many ways we could take that question from, you know, if I have my McInnes CRC hat on, then I'm straight away thinking about technologies themselves. And from the AuScope perspective, I could be thinking about data and how we actually would use big data. But just to throw something, I'll go with the first option because data, machine learning, AI was discussed by all of the speakers, but technology hasn't been something that's really been necessarily a focus of any of the talks. And I think that if we actually want to be smarter, more efficient, and whatnot with, and kind of less costly with mining critical minerals into the future, then I think we actually need to think about what the mine of the future will look like. And the concept of a sample-free and a human-free mine, which sounds easy, but when you actually start to think about it, it's actually quite mind-blowing to think that industry is actually working towards and has a desire in the next 20 years to have a sample-free and human-free mine. That's going to require a lot of technology. It's going to require a lot of, that technology is going to be able to not only do the mining itself, but it's going to need to actually create data. So I don't know what the answer is in terms of the opportunity for AuScope specifically, but I think it's something that AuScope can actually keep its finger on the pulse in terms of what could be happening in that research space in future to see how we could actually fit into it.
Right, thank you. So maybe I'll ask sort of maybe Sandi and Michael the same question, but maybe given that you both work for large government-funded research organisations and engage with the research community, many of whom are represented here, I guess, what opportunities do you see for that engagement between your organisations and the sort of university-based research groups over that period?
First, I'll just sort of say that CSIRO works across industry and government and academia. And so the opportunities that we see, you need to sort of think about them in short, medium and long term. So really long term space, right? So where exploration through cover is 2 metres, okay? Now, and so we can say we can take learnings from them, but the actual fact is that space is taking learnings from us at the moment. So we're at that sort of stage. The short-term opportunities are probably in new technologies, but new technologies have to be underpinned by science, and we're not seeing that that's not adequate right now. So we've got a lot of new sensors on board, for example, and the data coming from them is just awful. Okay, or you can't get what you need from the data, or the software solutions that come with the sensors are really slow and they're no good for production. And so there's some really good opportunities, I think, in production, because that's the very fast part of a mine, and unblocking so helping with their decision support in that space will actually then go back into a bunch of other things that we're developing. So I think there are opportunities in software solutions or AI there, but also underpinned by real science. And in terms of the science part, it's GeoMet. It's just not done properly. So, and I think that will actually uplift the extraction for us. So yeah, GeoMet. And the kinds of sensors that I talked about, like, so, in terms of exploration or even at mine, better geophysical sensing tools, better mineralogical sensing tools downhole, that kind of thing. But but all talking to GeoMet.
Okay. I think when we're talking about critical minerals, what we're really talking about is speed. So when a critical mineral becomes a priority for the government, it's in reaction to something that you'll hear in the news, and it's like, where can we get this mineral now? So all of the long-term science that is being presented up here is really great, and that's going to secure the next couple of decades. But when, I think, going to Carolyn's point about data, I still see a lot of 20-year-old practices in terms of data handling and data management where it takes time, and there's huge lead times for everyone involved, including industry, exploration industry, and everyone else who are not upskilled enough to use some of the data that we're producing. And I think what we really need to tackle in terms of short-term wins is reducing that lead time for ingesting our data and science into be able to use it to make decisions more quickly. Because when we're talking about critical minerals, what we're talking about in terms of science can apply to pretty much every mineral and every bit of geoscience. But critical minerals specifically, we're talking about getting things done faster and identifying those minerals faster, getting them into supply chains faster, building resilience into those supply chains, and that requires to be just better at doing things quickly.
Right, thank you. So maybe, yeah, you did.
Okay,
yeah.
cool.
Yeah, there's going to be lots more questions, I'm sure. Make sure you're all thinking of questions. I've got one more for my two AuScope colleagues, so for Brent and Graham. I guess from your perspectives, I guess what are the opportunities, building on what's been discussed, but also what are the opportunities for collaboration that you see? Brent, you're running a new collaborative project. You're also involved with Microscopy Australia, another NCRIS organisation. What are the opportunities for us to connect with other groups? And similarly for Graham, who's working across lots of different organisations, how should we better do that? And what's the role that you could see that AuScope could play in doing that better?
Sure. Well, Tim, I think there's no better time for AuScope to be relevant in the national research infrastructure space because, critical minerals are it, baby. I mean, we're in a good position, and everything that we've done so far has been working towards this moment. A lot of the work that we've done earlier was very, I would say, not necessarily applied, but we've always had that opportunity. And I think a lot of the work that's been done now, we're in a position to capitalize on that and to show a leadership role with government, but also to bring along the other NCRIS capabilities together with us. For example, Microscopy Australia, as you mentioned, clearly they're key allies in terms of analytical and laboratory environments. Any of the, offshore is going to be an area where people are looking for critical minerals, whether we like it or not. So if there's ways that we can help with that and make sure it's done environmentally sustainable, I think that would be a great place to show leadership. But I think that overall we have fantastic capability that exists, but it exists on the thread of uncertainty around student numbers. I think that is an existential crisis that we currently have. Are we inspiring the next generation to come into earth sciences? And that's, for universities, obviously, as a key role for them to play. But overall, as a country, I mean, we're talking about spending hundreds of millions of dollars to put a Band-Aid on smelters around the country, which are critical. But at the same time, we're abandoning I think we're abandoning the youth of the country in terms of a career, showing them viable careers in earth sciences. So I think we have a role there to play as well in terms of the human capital as well as the research infrastructure.
Great answer. Graham, do you want to add to that?
Yeah, thanks, Tim. I'm just going to give a slightly different perspective. I'm just reflecting back maybe a decade ago. We were within AuScope, probably a bit too insular in our discipline areas, and maybe I'm guilty of this too, showing a resistivity model or a seismic model or the geochemical maps and so on. And I have seen an enormous development over the last few years in integration of those, and I was very impressed by Brent's work with Dietmar's group on combining that mineral prospectivity with the four-dimensional geodynamic frameworks and the predictive elements. And I guess I'd like to see that just continually to develop and just get more closer collaboration, because ultimately we only have one Earth and everything we measure is of that Earth. So we can't be delivering separate products that really have singular outcomes and therefore only engage some part of the community. So I think partly then part of our brief as AuScope is to talk more, and this is one aspect, I guess, being here at this conference. But I think also then is to ensure that what we do, we understand, of course, but that whether our industry colleagues also can have access to that information, can use that information. So I think there's a communication component that we really have to make sure that we are fully compliant on, because if we're developing new technologies and ideas, we can't wait for the publication cycle to take 1.5 years for the paper to get published in a journal that no one reads. We have to make sure that everybody knows what these outcomes are.
It's almost like that was a Dorothy Dixer around translation. Nicely done, Graham. Okay, Caroline, do you want to just add anything to Brent's existential threat comment? Because I know that that's an area close to your heart.
It is. So in terms of the future workforce, I think that, yes, that you could call it an existential threat if we wanted to be quite dramatic about it. But when it comes to future workforce, I think, and what I might do is answer that from the perspective of AI, so that we see that AI is something that we need to incorporate into everything that we're doing within AuScope. We are, as Graham just said, all of these different types of data sets that we need to be able to integrate together. And we're producing so much data that the logical thing to do is to use AI and machine learning so that we can almost automate interpretation of that. So one might then say, well, that means that a geologist is going to become redundant. I don't think that that is the case at all, and that if anything, that we need to be able to teach people or to encourage people to still come and do earth sciences, because yes, those jobs will be here, because it's not that codifiable knowledge that that AI, yes, it will be doing, but what that future workforce brings to the table is the tacit knowledge. It's the knowledge that can't be spoken, it can't be written. It's things such as critical thinking, emotional intelligence, creativity, entrepreneurship, all of that kind of thing. And that's, I think, a massive opportunity for the future workforce within the geosciences that I hope will actually, if we can communicate that, then I hope that will attract people into our community.
Please, yeah, thanks, Sandy.
So with my Australian Geoscience Council hat on, what we found with declining numbers in a survey last year was that in terms of students going into earth sciences at universities, we asked students in year 11, first and third year at universities what helped them decide what to do. Many of them that were surveyed didn't even know what geoscience was. Okay, so that was particularly in high school. They had no awareness of this discipline, and so when you don't have an awareness of it, then you just don't do it, right? So that's one of the issues. But the big drivers for them, the things that helped them make their decisions, were websites, university websites, because that is seen as a trusted source of information. So there is a real opportunity there to uplift that. Lesser drivers, advertising, they don't see it. They don't see the ads that BHP or Rio put out or whatever. Like only 11%, I think, see it, or 17%, so very, very low. So it's family and friends, university websites. The universities topped really high in terms of any information coming from universities, open days at universities. That's what will help to drive numbers up, and also then just education into teachers in primary school and high school. So we can talk about tacit knowledge that we need, you can talk about AI, blah, blah, blah. We are not going to solve this crisis unless we look at primary school and secondary school students.
Encourage you all to go to see Miss Talk this afternoon, wherever she is. Okay, any questions from the audience for any of our panel members? Please put your hands up. Surely we've got a question or a comment. Richard's got one at the back.
Thanks, Tim. Just on both critical minerals and translation, obviously it's the industry we need to translate to. They're the ones who would be the users. I don't think we've got many or any from industry here. Suggestions from the panel on how we could improve in that and therefore have a better translation story to tell our funders. Because we've got a great opportunity to say the downward-looking telescope is focusing on critical minerals, but it's perhaps just not there in terms of credibility at the minute. So any suggestions for help in that would be terrific.
Most of the exploration is done in this country by junior explorers, and I think trying to capture junior explorers into an audience like this would actually not be a bad idea. They do find the deposits, and then some of them even take things through to mine. I wouldn't bother with BHP, Rio, Newmont, any of them. They're not going to change their practices based on what AuScope does. But the work that AuScope does and serves, like the MT, like the EarthBank, the uplift around success with that sort of data for your junior and medium-sized explorers would be enormous. So maybe some sort of, we just need to reach out and invite them, I'd say.
Yeah, I completely agree with Sandy there. And this kind of goes to my previous point on speed. If you see some of these junior explorers, the software they use, the way they operate, it can be, and I don't mean to be insulting here, a little bit primitive. And you're thinking, why don't you use this data product? Why don't you use this that we've got? And they don't know. And so inviting them to forums like this, if possible, and we're trying to do this at Geoscience Australia through our new initiative, is to have them in the room and say, these are the products we've delivered, here's how you use them in your tool chain, whatever that tool chain might be, and this is how you can use it to find the next big discovery, hopefully. And then also, convey that our partners can do that as well, not be so focused on what GA is doing. So, say AuScope's got this, here's all the things we can do using the science we've delivered.
Yeah, I'd like to just point to two areas where we are delivering on that. So one of the issues in the university environment, obviously, is the publisher paradigm. Whatever we do in AuScope, we need to support that. We need to make sure that we get the best and brightest people working on the projects, and their success is based on publications. But the paradigm, where it falls down, is that industry doesn't have time to read the publications, or they don't want to, and the junior sector doesn't want to pay the $50 fee or whatever it is to get access to it. So that's why we developed the EarthBank project the way it is. So we actually do both. We help support the publication process, but also we make the data available from those publications. And the other interesting aspect of the analytical community is that we've done a straw poll, and we know that only about 1 in 4 days of analytical time ever actually gets published. So there's a huge inefficiency built into geochemical analysis. For whatever reason, people have children, people get different jobs, and never get around to publishing it. And we're trying to circumvent that and making that data available because it was largely paid for by the public. So that's one key aspect where you can actually support both sides of academia and industry research. The other thing is, I think one thing Australia is really great at, and GA and the state surveys are great at, is pre-competitive data sets. And I think whatever we do with our analytical facilities, and that's why we're trying to scale up and make sure we have 11 universities doing the same thing the same way, is that we can support the generation of pre-competitive data sets. I think that's really important for exploration companies, the smaller sector in particular. We know from the Heavy Mineral Map of Australia, which was a collaboration between Curtin and Geoscience Australia, we generated that Heavy Mineral Map of Australia in record time, like less than a year, using one single instrument. And we do know that there were multiple tenements taken out on the basis of that. So I think we're already doing that sort of stuff. We just need to tell the story better.
I'll comment from a McInnes CRC perspective, and given that, AuScope is an affiliate of McInnes CRC, so I think it's also quite relevant to this forum. In terms of research translation, we can think that within McInnes and DET CRC before that, we're going to have a cumulative 18 years of research into development of technology for faster, cheaper, more environmentally friendly mineral exploration. And what we need to ensure is that all of those products, all of those outcomes, and all of that research is actually translated into industry practices and processes. And I think that there's an opportunity there for AuScope, and it's something that we talked about yesterday, and we also talked about in the McInnes annual conference last week, is if and how AuScope could support pulling that technology through into so it can be used by industry. So we had a conversation with the geological surveys, and they were quite interested in the idea of AuScope potentially supporting some of those McInnes technologies so that the geological surveys themselves, who have been doing a lot of drilling over the last decade or so, but they would actually be able to use the McInnes drill rig, and then also those sensors that we've been developing on the back of the drill rig. So that, I think, is an opportunity for AuScope in terms of research translation into industry.
Got time for one more question or comment from the floor? Yes, at the back.
Hey, I'm from Geoscience Australia. My name's Anand. Not that any of that's important. I'm just agreeing with what Carolyn and Sandi have said about, like the science being important, and also how, no, I don't think geologists' jobs are going to be taken over by AI, because I'm a geophysicist. And what I'm finding in our use of AI, and I'm sure that I'm not the only one who's doing this, so after I finish saying I have to say in the next 30 seconds or so, I hope there'll be other people that nod in acknowledgement with me. When you use AI to do stuff that you might have taken 15 minutes to do, you might be taking a minute to do now, right? You ask it to look at a formula and then be like, can you do these steps for me? And it does it fairly quickly and very confidently. And I've been using some of these GPT models that we've been asked to use at our workplace, so it's all certified, it's all good. And I was doing this thing where I'd come across a problem I hadn't quite come across before. There's something I needed to minimize. Bear with me, I'm not going to talk math. And I needed to do some differentiation, but it was a real objective function, but some of the elements within it were complex. And I was like, how do I do this? I have to go back to complex differentiation, and I don't remember it. So I asked it to do it for me, and then at the end it gave me an answer, but it didn't quite look right. The dimensions weren't right. And so then I sort of had to go back and do it again, and then I had to query the steps, and then it said, I'm really sorry I made this mistake. Well, here's what it really should be. And it was very apologetic about it, but if I hadn't sort of, thought, wait a second, that doesn't quite look right, and I hadn't queried it again, and I could do this because I'd studied this in the past, and I have some still, thankfully, remnant of critical thinking remaining, I was able to challenge what, the GPT model told me. And I worry that in our rush to develop prospects or in our rush to deliver on the science, we're just doing things and we're not asking those questions, or maybe we've forgotten, like I barely remember the stuff that I should know. and this is a problem. So I think more than ever, now is the time when we need to brush up on those fundamentals and make sure that the people that are coming through, year 12 or the universities are actually clear on the fundamentals, because it's going to get very muddied very fast. So that's kind of my experience.
It's an excellent comment.
Look, I'm in the education space. We are at this frontier of where students are basically using AI every day. And I think the distinguishing between a student's work and an AI work has become increasingly complex, and we've actually gone back in history, and now we have formal big exams in big halls because it's the only way we can evaluate the student's knowledge. I think and your arguments are fantastic. It's the implementation of trying to ensure that the students do have that fundamental background is going to be a big challenge in the education space, and I don't have an answer for it, unfortunately.
The education sector aside, where I think it is a real problem, I think it's also a real problem for early career researchers who tend to do things that can maybe be done competently by AI or competently enough. So, basic data entry, those kinds of data compilation questions. If we get our natural language processing sophistication good enough, we can just compile data from reports and not get junior scientists to do that. And that cuts out the bottom end. So people graduate and they've got the skills, but then they're not given the jobs because, we're doing that with AI. We don't need to pay someone $60,000 a year. We can do it with some sort of GPT that will extract that table and put that into a database kind of thing. That, I think, is the real issue because, and I think this is not just unique to sciences as well, I've heard it's happening in law and those kinds of applications where you might get a paralegal or someone very junior clerk to do this kind of thing, and they're just getting GPT to summarise a contract or something like that. And those early career lawyers, they need to have that experience in reading those contracts or reading the legislation. I think that's probably the darker issue. I think you'll still be able to tell whether my brother's in an academic and he's teaching people and he's like, he can spot it. He knows he can spot it. One time he spotted it because they left the emojis in it from ChatGPT. But I'm more worried about cutting out that bottom end who's coming in early career. But I try, and so, sorry to take too much time, but I try to, with some of my junior staffers, to encourage them to use AI as a bootstrapping exercise to learn something new. So if you want to learn how to code Python, you've never done it before, test yourself, run the code. The code will tell you if it doesn't work and it'll give you outputs that you can check, but that's not going to replace proper learning. So you'll need to just, I think it's good for bootstrapping new ways of learning and new ways of thinking, basically like Google on steroids, but it's not going to replace actual work in that regard.
Thank you. Final comment from Brent.
Okay, well, look, AI is research infrastructure, right? So we got to be in it. I just came back from a meeting in China. Two things. China University of Petroleum, I visited, gave a presentation on EarthBank, and they have 27,000 students. at this one university, 7,000 PhD students. They are actually, this institution is actually building its own large language model to encapsulate, to grab all of the information that's ever been generated in that institute. And that's part of their strategy. And so it has to be part of our strategy, I think, as well. There is a company formed in China, and the Chinese government there's a lot of incentivization happening right now in China to bring in academic companies. And they are called GeoGPT. And they have 100 data scientists operating in that company. And they are trying to basically suck up every paper publication, every bit of geological knowledge. So that's what we're competing against. I think we should do something ourselves.
Good positive note to end. Dietmar, you've got one.
Always make their answer seem confident, irrespective of how right or wrong it might be. Because if they were to let the user know how uncertain these answers are, they will stop using it and it would cut into their profits. So it's in their interest that it always seems confident, right? And I think it's important that everyone is aware of that. Right?
That's a great way to finish. I think that summarizes my whole lecturing career, Dietmar. My wife can tell when I'm lying because I put my lecturing voice on, well, not when I'm lying, but when I don't know what I'm talking about, because I sound much more confident when I don't know what I'm talking about. Thank you all so much for that. Now, we've got a couple of things that we're going to do before we let you break for lunch. Dave's going to run a little exercise very briefly about getting to know somebody who's around you, and then we're going to do a photograph with everybody up the front. So I'm going to hand over to Dave. I want to before we do, thank everyone on our panel for their input today.
And Tim, let's do a very quick photo of you and the panel before you guys break, if that's okay. There we go, love it. All right.